Meet the second revision prototype cutover laser. This build is known as the LazoBlade and is designed for high speed, accuracy, and reliability, implementing optics suitable for deployment in lines cutting up to 8-meter rolls of 200-gauge polyester film. The attachable fume chamber captures vapor particles for analysis of concentration values. Let's go through the build, reviewing how and why each component was made or selected. The frame of the LazoBlade is constructed from extruded T-slot aluminum, chosen for its versatility and strength. The laser and mirror mounts are off-the-shelf components capable of precision adjustment. The mirror mounts house molybdenum reflectors, which are capable of redirecting 10.6 micrometer wavelength with a nominal efficiency greater than 99%. The laser tube is a 40-watt water-cooled CO2 type, selected for its superior absorption by polyester material. The beam expander is mounted on a beam combiner. The combiner projects a visible red laser collinear to the CO2 beam. The expander triples the diameter of both beams, reducing the hazard by lowering the power density, while at the same time decreasing the beam divergence by a factor of 3. The laser head houses both the final reflector as well as the focusing lens, with a 100mm focal length. This provides the greatest length of laser energy concentration to compensate for any material deviation. The laser head is mounted on a custom CNC machine carriage. Utilizing polycarbonate and ball bearing V-wheels and riding along an open rail design. This provides minimal resistance while maintaining precise laser head accuracy during linear motion. A 200 step per revolution stepper motor belt drives the carriage to achieve linear motion. The motor produces 2.2 Newton meters of holding torque and an effective driving force through 2000 RPM. Along with the matched driver, the motor is capable of moving the carriage up to 2 meters per second. The high speed achievable by the carriage requires a number of safety mechanisms. Limit switches trigger an SR latch, disabling the stepper driver in the event of an overrun. This requires a manual reset. Secondary to the electronic shutdown, stop blocks enforce a hard limit. The material mounting rack supports a 1-meter roll of polyester film. The stanchions are fully adjustable to accommodate various positions for testing. The top crossbeam creates a narrow passage between the layers of film, demonstrating the versatility of the beam catch. The fume chamber is a length of clear 4-inch diameter PVC pipe, allowing for visualization of the specimen. One end cap is precision machined to fit the lens tube with an airtight seal. The other cap is fitted with a black anodized heatsink to absorb the residual beam energy. The sample stand is CNC machined from oak, implementing 4 neodymium magnets, enabling adjustment of the stand from outside the sealed chamber. The power measuring block is 6061 T6 aluminum, anodized and explicitly dyed for maximum energy absorption and resilience to the CO2 laser beam. The block's mass was precisely measured for accurate power calculation. A thermocouple is fitted in the core of the block, packed with silver thermal compound to efficiently transfer heat to the sensor. Now to review the testing and some preliminary results. Masking tape and thermal paper were used to register markings of different beam concentrations requiring varied sensitivities. The expanded beam can be clearly observed during the marking process. Beam alignment was a precarious task, taking great patience to get the final exit beam exactly perpendicular to the plane of the focusing lens. Firing the laser for a given time at the measuring block of known mass and specific heat allows for the calculation of usable power. Taking this measurement using the 40-watt CO2 laser results in a real power output of 28 watts. When measuring the carbon monoxide byproduct of vaporized polyester by use of a CO meter inside the testing chamber, low values were recorded. A cut diameter of 8 mm in 200 gauge polyester was necessary to increase the concentration of the chamber by 1 part per million. This data will be used to calculate the carbon monoxide released from a full-length cut to a given room size. Some initial cutting by the LazoBlade revealed an excellent edge with no contact of the film. Further testing with varied parameters will yield faster and more refined cuts.